Garrett, did you want to start?
Yeah, thank you. Nice to see you, Sarah.
Good to see you too.
Hello, Pakadarmanto. Hello to everyone from BPS and to all of my colleagues from USDA NAS and also to our other colleagues joining us from Indonesia, from Ministry of Agriculture, from other agencies. I'm not sure if Bapanas is on this call or not, but I do understand we have some new participants that are joining us today who have not possibly been on some of the previous web chats, the webinars that we've been having. So I just wanted to say a few words at the beginning. I'm Garrett McDonald. I'm the Agricultural Attaché at the U.S. Embassy in Jakarta. And so for those of you who are just joining us for the first time, thank you very much for your participation in this series. I want to make sure to stress that this series is happening online because of the current conditions with international travel, and that our intention was to hold this training session in much more depth in person in Jakarta and in other parts of Indonesia for certain parts of field travel, but we're currently unable to do that. So this training session is not meant to replace that in-person training, but what it is meant is to give us an opportunity to start to learn a little bit more about how BPS operates, and for BPS to learn a little bit more how NAS operates. And I know that and today we're beginning a session on remote sensing. We previously did a training session on the GADIS online software program. And we also worked on area frame surveys. So this session I know is going to have a lot of detail to it. I know that it could easily be a full week worth of work because there's a lot of, just from the amount that I know, there could be a week worth of information. NAS does a lot of work on remote sensing. I'm sure that Sarah and her colleagues may be getting into the crop data layer in some detail and how that factors into assessing agricultural production and conditions. And I really do think that NAS is at the forefront in how they're using remote sensing to better improve agricultural data in general. So I really am looking forward to the next several weeks of classes. I did want to say that at the end of the remote sensing session, we will send out a survey, and I would greatly appreciate it if everyone who is joining the classes would take the moment to respond to that survey. It helps us to implement these programs and to get funding and to find better ways to improve these programs going forward. So give us your honest feedback and assessment. It won't take but a few minutes of your time, but it really helps us a great deal. And in that same line of thought, I want to mention, because I'm actually on travel this week and will not be able to join the session later on Thursday morning Indonesia time, that we will have a guest from our Foreign Agricultural Service in Washington, D.C., who works in the section that helps to administrate these programs. His name is Lawrence Truba, and he will give a few comments about the work that they do at the outset. And so, Sarah, that's a heads up for you too. So thank you for helping and welcoming Lawrence. And as always, I want to thank my colleague, Ibu Ugi, who is also joining these sessions and has been a great assistant in passing along the information for the invitations, for the video recordings, and of course the questions that we've been sending back and forth between USDA and BPS. So thank you, Ugi. I know many of you have received an email from her, possibly with the invitation, but please do, if you have a question, reach out to her. She is based in Jakarta and is our agricultural specialist at the US Embassy. So with that, I will pass it back, but I just wanted to welcome, say a few remarks to welcome people this morning, because I know that some of you, it's the first time joining. So thank you so much for taking the time to join. I've heard great things and really enjoyed the sessions I've been able to participate in thus far, and look forward to rejoining some of the sessions in the following weeks. So thank you very much, Sarah. I'll pass it back to you.
Thank you, Garrett. Thank you. For those of you who do not know me, my name is Sarah Hoffman. I'm with the National Agricultural Statistics Service International Program Office, and I've been both a presenter as well as the coordinator for these sessions. Tonight, as Garrett mentioned, we are going to be delving into remote sensing. And to help us out with that, I have tapped into our Spatial Analysis Research section folks here at NAS. They do a lot of remote sensing. And tonight's presenter, before I get to presenter, if you have questions during the session, please add them to the chat. And then at the end of Avery's presentation, pardon the tail, at the end of the presentation, I will read them out and we'll get some answers for those. All right, so our presenter tonight is Avery Sanborn. She's a geospatial analyst at NAS, and she's worked there for almost 5 years. Along with the rest of the spatial analysis research section, she helps to produce the Cropland data layer, which provides freely available national agricultural land cover data to both internal and external customers of USDA. Avery also helps create cartographic products related to the Cropland data layer during national agricultural disaster events such as hurricanes and wildfires. And I should mention that the US is expecting to have a hurricane make landfall this week. She works with the disaster monitoring team to produce disaster analysis reports, maps, and data in near real time. And hopefully she'll be sharing all that on Thursday morning. She's also worked internationally. In 2018, she traveled to Port-au-Prince in Haiti to assist in international capacity building programs focused on GIS, remote sensing, and land cover classifications. So Avery, if you'd like to take over.
Sure, thanks, Sarah. Let me share my screen. Let's see. All right. Can you guys see my slides? Okay. And you can hear me okay?
Yes.
Okay, great. Let's make them full screen. Okay. All right. So yes, as Sarah mentioned, I am a statistician and spatial analyst at USDA. And one of my roles includes remote sensing for monitoring crop production in the United States. So within NAS, National Agricultural Statistics Service, that is the statistical arm of the USDA, and NAS collects, disseminates data on all facets of US agriculture. Their mission statement is to provide timely, accurate, and useful statistics in service to US agriculture. And then within NAS, I'm part of the Research and Development Division, RDD. And RDD helps to produce national, state, and county level estimates, crop estimates each year. And we develop methodologies and tools to improve NASA's ability to collect, manage, and disseminate data. And so one way that we can help do this is through remote sensing and GIS. And my group within Research and Development Division is what Sarah mentioned, SARS, or Spatial Analysis Research Section. And this group is comprised of geographers, cartographers, IT people, programmers, and statisticians. Yeah, so that's just a brief overview for those of you who may be joining for the first time today. So, oh no, I went too far. No, sorry, there's a lag on my screen. Let me go back. Okay, you should be seeing the Cropland data layer, or I'll refer to it, the CDL, for the duration of this program, of this presentation. So one of the spatial analysis research section's main products, our flagship product, is called the Cropland Data Layer, the CDL. And I know you may have heard about the CDL in a few other presentations last month or this past month, but I'm just going to, for now, this is going to be a deep dive into how we create the CDL and what it's used for. As an overview, it's a raster georeferenced crop-specific land cover product that is produced both seasonally and annually for the entire continuous United States. So the 48 states that you see here. Some people like to call it a census by satellite. And in the legend, you can see the types of crops that are identified in the CDL, which are in this map in order of decreasing acreage. So if you can't read the small text, some of the largest crops that the US grows and the ones that have the most acreage in the US are corn, soybeans, and winter wheat. There's also smaller crop categories such as oats, let's see, grapes, oranges, blueberries, cherries, all sorts of specialty crops. And there's also a couple different types of double cropping categories. So sometimes when farmers will plant 2 different crops in the same season, we can identify those. And then the CDL also identifies larger, broader categories of other land cover that's not agricultural. So you'll see forest, shrubland, developed wetlands, water, and barren areas also in the CDL, just to fill in the rest of the space that is not agriculture. Okay, so the goals of the CDL program include combining remotely sensed imagery, Farm Service Agency data, and NASA survey data to produce supplemental and unbiased acreage estimates for major commodities in the US. And this is showing planted crops, not harvested crops. So we're only mapping planted area right now. We produce crop-specific digital land cover data in industry standard formats for all levels and all different types of users. And these goals comply with NASA's mission statement to provide timely, accurate, and useful statistics in service to US agriculture. So this is an example of a state-level cropland data layer. This is the state of Ohio from 2015. You can just start to get a feel for what types of crops a certain state might produce. So in this instance, you'll see the dark green areas are soybean fields and the golden areas are corn. And then if you go down to the county level, which is the next division below state, let's see, okay, here's an example of county from Ohio. You can start to actually pick out individual fields or roads or waterways, things like that. And you can just start to see more detail when you get down to the county level. Let's see, what did I miss? All right, so now that I've told you exactly like what the CDL is, we can get more into the specifics of it. So like I said, we cover the entire 48 states, and we've done this since year 2008. Some states have longer coverage, but as a whole, it's all been done since 2008. So going on 12, 13 years now. They are produced and released annually. So for example, the 2019 Cropland Data Layer was released in early 2020. And we're currently working on the 2020 Cropland Data Layer, and that'll be released once in 2021. We also produce Cropland Data Layers within season. So we'll do a June Cropland Data Layer, an August Cropland Data Layer, September, etc. So we'll do each of those with like each month, we'll do some states each of those months. But those all stay internal. Those never get released to the public. And the Cropland Data Layer is at a 30-meter spatial resolution, and that has been 30 meters since 2010, I believe. And that's because we rely heavily on the Landsat data, which is a 30-meter resolution. Before 2010, it was released, I guess actually before 2008 now, it was released at a 56-meter resolution. And that was when Landsat was not free and we used a different satellite sensor then. So it very heavily relies on what satellites we're using. Let's see. There's standardized colors, standardized names, projections, and of course we release metadata. Everything is easy to understand across state and county boundaries. And there's over 100 different cropland categories, like I mentioned earlier. And they can all be used in a variety of applications, which I'll also get to at the end of the presentation. And you'll hear about disaster applications on Wednesday night, Thursday morning. So now I want to go over the CDL processing flow. This is an overview slide, and we'll get to each individual piece in the next few slides. But as an overview, first we look at input data. So this includes selecting satellite imagery. So you want to select cloud-free and a good spread of imagery over the season and over the state. And we use a variety of different satellites now. We have ancillary data, which is extra layers that we input into our models, such as a tree canopy layer from the U.S. Geological Survey, USGS. There's an impervious layer, elevation data sets, things like that. And then ground reference data, which is what we use to train and validate our models and check our work. Once we have all of our data compiled, we'll start to sample that data for training and validation. And we'll sample that stack of imagery to get those training and validation points. We use a program called C5 next, which is a decision tree software. So it's data mining the samples and it derives the best fitting decision rules. And then we'll make a classification using a software called AirDAS Imagine. The one I have on here is from 2011. I think we're up to 2018 now, but it all does the same thing. Yeah, and so we apply those decision tree rules to our classification. And then our final output is a classification, and we'll put that into map form and using ArcMap or whatever mapping software that we have. And of course, we'll do an accuracy assessment on all of this and derive acreage estimates from this as well. So now that you know the overview of how we create the CDL, I'm going to get into each individual piece now. So the first thing I mentioned was selecting satellite imagery. Right now we're using Landsat 8 satellite imagery, which you can view more information on the link that's provided on the slide. It launched in 2013. It revisits the same area for us every 16 days. It has 30-meter resolution, and there's lots of different multispectral bands to choose from when you're deciding what imagery to use. Let's see. And all of this Landsat data is, of course, available online for free. The next slide has an example of a 2-week cycle. So those 16 days, those 14 to 16 days of Landsat imagery. So this is an example of, in 2 weeks, what kind of imagery can we get over the entire US? As you can see, sometimes there's clouds, so we always rely on more imagery. Like we always want to go through the whole season and see if you can find cloud-free imagery. But sometimes it is very cloudy, so we'll rely on other imagery, such as Sentinel-2 imagery. This we started implementing more recently, like the last 2 or 3 years, I think. Sentinel-2 is also free. It's from the European Space Agency, the ESA. It also has a selection of lots of different bands to choose from. It has a faster temporal resolution. It's got spatial resolution. It's better than Landsat at 10 meter and 20 meter. But since we still rely on Landsat, we will resample this up to 30 meter to match. And of course, like I said, it was free. It's also available online. We do use a few other satellites that are not free, such as the DMC, the Disaster Monitoring Constellation. This one is not as, the orbit is not as regular as Landsat or Sentinel. So it's not as reliable to get imagery throughout the whole season. And there's not as many bands as well, but sometimes it comes in useful also when there's clouds. Okay, so that's the imagery. Now I want to talk about our training and validation data, our ground reference data. So we have two categories of this, agricultural and non-agricultural. And this is a critical component for any type of remote sensing program. So NASA is very fortunate to have available administrative data from the USDA FSA, Farm Service Agency. So the USDA Farm Service Agency has a program that's called the Common Land Unit, and that's basically a GIS format ready data set for us to use, where farmers will report what kind of crops they are planning to grow or they planted. And then once they do that, they get to participate in different government programs, such as crop insurance, things like that. But FSA data does contain sensitive personal information about farms and about farmers, so that's not able to be publicly released, which is why we use this as training data and then derive our own classification. Beyond agricultural, so non-agricultural ground reference data, that comes from the USGS National Land Cover Dataset, the NLCD, and this is updated every 5 years. This slide is out of date. The latest is from 2016, and they're working on, I guess, the 2021, or eventually they'll get to the 2021 NLCD. So in 2 or 3 years, we'll have a new updated non-agricultural data set to use. It's not perfect, but we need this because not everything is agriculture in the United States. So we definitely want to be able to fill in the gaps for forest, wetlands, water, developed areas, etc. Another type of input is the ancillary data sets. And this comes in the form of supplemental ground reference data. So I just want to mention that NASA also has access to these types of data sets to help refine our cropland data layer. So these data layers will help us to gather information on specialty crops and other farmers and growers that may not necessarily report to the USDA what they're growing. So anywhere where we may have gaps in our knowledge and in our ground truthing. So for example, there is vineyard data from Land IQ in California, which is shown in the pink. Those tend to be things like grapes and other specialty crops. We get citrus data set in Florida, and just other types of crops and things that you can see here. And this, on the next slide, I have an example of what the CDL may have looked like with no additional ground reference data in California, which is on the left, versus on the right when you have the additional ground reference data. So in the purple, that's grapes for us, and this is a big grape growing region. And so not these types of growers don't necessarily report to the USDA, but with this extra data set, we're able to capture those grape fields, or yes, those grape fields. I was gonna say wine fields, but that's not right. Yes, so that's an example of how this helps our CDL. And of course, we did accuracy assessments on those. I think those are not on this slide though. There's also crop-specific masks, which is areas that we also know are trouble spots usually. So for example, in Indiana, you'll see that there are Amish area masks. I have an example zooming in Indiana. There's a big population of Amish people, and they tend to not rely upon the government subsidies, and therefore they don't report to the USDA what they grow. And so since we lack the training and ground reference data there, the computer really has a difficult time classifying. And that's what you see on the left-hand side of the image, where there's no extra data sets. But on the right, we create a mask that helps to define alfalfa in this area, which is shown in the light pink color. So you can see we're capturing alfalfa better when we have crop-specific masks in place. Okay, so now that I've talked about all of the input data, so it's imagery, the ground reference data, the ancillary data sets, we can talk about a brief summary of how the classification works. So on the left of this slide, you can see 4 months going up and down of false color infrared imagery. In this imagery, the bright red areas indicate vegetation or very green vegetation. So you can see that as the months go on, so April, May, June, and July, as the months go on, the crops become more visible in the infrared imagery. On the right, you can see that the imagery in August on the top, you can see that with some of our ground reference information overlaid on top. So for example, the teal or the green area represents almonds, and you can see those fields delineated in the first circle. You can also see the pink area, the light pink area is alfalfa, which you can also see some fields delineated in this picture. So basically what you're doing is you're taking all of your imagery and your data and you're figuring out what is being grown in that imagery in that field. So we know the imagery under the almond fields in the teal color. The computer, you can tell the computer that's almonds, and then it will identify other fields in the imagery that look the same as those almond fields. And it'll do this for all the different types of crops that you give it. We call these signatures in remote sensing classification. So in the bottom image, you can see that our classifier has found more areas of these almonds and these alfalfa fields. And it's found similar fields and they have similar properties. So it identifies all the fields that it thinks are almonds and alfalfa and corn and cotton and all these different fields. Once we have the final classification, which is what you see on the bottom, we'll do an accuracy assessment on it, of course. So accuracy does vary by crop. Dominant crops in the landscape, such as corn and soybeans for the US, they tend to have a higher accuracy, but less dominant crops, they're not as accurate. We assess accuracy for non-crop categories using the US Geological Survey and LCD categories, but this is less accurate since their classification also has some degrees of error in it, so there's that. And then we calculate overall accuracy as well as producers and users accuracy. So producers accuracy, which is the first red box that you see highlighted, corresponds to errors of omission. So this is when the model leaves out some of the real cornfields from your corn category. So it's underestimating. And then users accuracy, which is highlighted in the second red box, corresponds to errors of inclusion or commission. So that's when the model accidentally includes grassland in the corn category. So it's overestimating how much corn is in this category when it really shouldn't be in that category. You don't necessarily need to know the difference between these. It's just when you are a geographer, you would use those to help determine if you're overclassifying or underclassifying certain crops. Let's see. So once we have our land cover classification and we have our final CDL, we will perform a regression on this, because one of the main reasons that we create the CDL is to assist in the estimation of acreage area. So we don't just want to count the number of pixels in the categories, because we know that's not perfect, and we know there's some bias, there's some error in there. So we want to do the regression to derive our acreage estimates. So this is an example of one of our segments, which you've probably heard some of my colleagues talk about in previous previous presentations. But basically a segment is an area of land that has been enumerated in a survey, like a handwritten survey. So basically on the left, you'll see the survey that someone filled out, and they'll say, in this case, they'll say there were 227 acres of soybeans in this area and 337 acres of wheat in this area. So if you go to the same area in our map, though, you might see different numbers. So for example, in our example, from our map, we calculated 273 classified acres of soybeans and 541 acres of wheat. So in some cases, our acreages might match up, and that's good, but sometimes they'll vary greatly. So in this case, wheat is very different between the survey and our land cover classification. So what we need to do is perform the regression, which you'll see here on the graph. So we plot all of those segment counts on our graph. And we look at the relationship between the survey acres and the land cover acres. So we use this to counteract any sort of bias that we have. So in this example, on the x-axis, you'll see the CDL, the classified acres, and on the y-axis, you'll see the survey acres. In a perfect world, all of your segments would line up on a perfect line going through the middle. But that's not always the case. As you can see here, there's always going to be some outliers or some differences. But you can see that when you graph this, this graph has an R squared of 0.950, which is pretty good. And this is an example for rice in Arkansas in September. But as you can see in the bottom right, we do this maybe 3 times a year. And the next month in October, the R squared value is going up a little bit. It's 0.957 now. So as we go throughout the season, our R squareds do get better. And that's why we do it. We do it multiple times throughout the year so that we're giving better estimates every time we do it. And then here you can also see some of the outliers in the different colors, blue, green, and yellow. And those will be removed from the regression as well. And these discrepancies could be due to any possible number of reasons. It could be farmers that decided to change what they planted. It could be errors in survey responding. We don't know. So there's lots of different reasons that these numbers don't line up. So of course, we'll create metadata before we put any of this data online. The metadata will have input data, it'll have accuracy tables, it'll have legend information, the methodology is documented, different things like that. And then once everything's ready to be published for the public, it will go on our portal called CropScape. And you can go to CropScape right now. All you need is an internet connection for this. CropScape is a web service-based interactive visualization of the CDL and all the historical CDLs and all the other products that come with it. So it is free to use. It is free to download CDL data from here. It's open to the public. You don't need any special software tools. All you need is your internet. And it has tons of functionality within the portal, or you can download the data and put it in your own GIS. So some of the functionality that we have on CropScape is similar to ArcGIS or QGIS. Basically, it gives you the ability to select a county or select a state that you're interested in. You can input your own polygon of interest. You can download a raster format of the data, or you can download a table in tabular format as a spreadsheet. You can do change analysis. You can swipe left and right to see the changes, things like that. So now that I've told you what the CDL is and how we made it, I want to show you some of the other applications being used in our own. So this is an example of crop frequency layers. This example is corn in the United States over an 11-year period from 2008 to 2018. This is showing how many years out of those 11 years corn has been planted. And so frequency in this case is defined as, the number of years a pixel was classified as a certain crop in the time range, regardless if it's consecutive years or it skips a year or whatever. So in this map, the darker colors, the blues and the purples, those are fields that have been corn almost every single year, versus the lighter colors, the yellows, those have only been corn once or twice out of that time range. And so this could be used for a number of reasons. We also have it in cotton, soybeans, and wheat right now. And then I'll show you another example of like a bivariate map. So this is showing the frequency of corn and soybeans. So anywhere where it's bright yellow means that it's been corn however many years. Anywhere where it's bright blue means it's been soybeans, but anywhere where it's a mix of the two colors, if it's green, it means that it's crop rotation, or it changed from corn to soybeans. And so you can zoom into those areas and figure out why that might be happening, or examine the changes that are taking place in your country. This is just another example for for corn and wheat, another different type of crop. Wheat's in the bright red, and then anywhere where it's orange is a mix of the two crops over this time range. Another,
Avery, you just froze on us. Avery? All right, so we're obviously having some technical difficulties with on Avery's end.
She just texted me and she is trying to reconnect. So she acknowledges the problem.
Okay.
For a couple seconds.
Okay, great. Well, this might be a good time if you have any questions to write them down in the chat. And hopefully Avery will be back with us shortly.
Can you hear me and see me now?
Yes, yes.
Okay, I'm sorry. I say all you need is an internet connection and mine fails. But okay, let me get it back up and running. I'm sorry about that. All right, can you see my PowerPoint again?
Yes, it's back up.
Okay, I am currently on the cultivated layer slide. Okay, so I just finished talking about the crop frequency layers. Now I want to talk about the cultivated layer. The cultivated layer is similar to the frequency layer. It takes 5 years of CDL data stacked together, the last 5 years, and it calculates if it's generally cultivated or generally non-cultivated. And so in this case, cultivated is defined as either any pixel that is identified as cultivated in 2 out of the last 5 years, or any pixel that was cultivated in the last year, the most recent year. So you're looking at, in general, what are the cultivated areas of the United States? right now. And so you can see how this changes throughout the years too. But this is useful in using for analysis to just understand in general what type of areas are affected by disasters. And it's used for a number of other researches as well. This is an example of crop yield estimation. I think you'll get this talk way more in depth than I can do it here by Dave Johnson in a couple weeks, I believe. But I'll just briefly mention it here because it is a big part of the programming that we do. This is looking at the yield of crops rather than just the area or the acreage of crops. The general idea, I think, of this is that you take your CDL and you isolate whatever crop you're looking at. In this case, we're looking at only corn. And you take just those corn pixels and you can overlay them on different types of imagery to understand how healthy that crop is, and different vegetation indices that will correlate with yield. Dave will get into this in another talk. So I'm not the person to ask about this, but just to give you an idea, we do yield analysis. I've also looked at crop migration in certain parts of the United States. This is an example where each dot represents the center of a crop area for a certain year. So there's 3 crops I'm identifying here: corn, soybeans, and spring wheat. And you can see the lighter colors in each crop are earlier years, the darker colors are later years, and you can see the center of this crop start to migrate different directions. So this can be used to identify if a crop area is expanding or getting smaller and things like that. And this could be due to any number of reasons as well, but that is something you'd have to look into yourself. Another example of migration and change is looking at what year was a crop first grown in this area of the United States. So in this map, this is talking about soybeans. And what you can see is that brown colors mean that soybean was grown really early in this time frame. So in this case, 2006 and 2007. But the bluer colors mean that soybeans was not grown until 2015. So this is actually identifying new areas of soybeans and older areas of soybeans. So it can also tell you like where soybeans are expanding in the US. I'll get into this presentation on Wednesday night or Thursday morning. This is about disaster analysis, monitoring disasters in the United States. The goal of this program is to assess how much cropland is affected by hurricanes, wildfires, heavy precipitation events, things like that in near real time. So we've developed this operational methodology using the freely available radar data, which can penetrate clouds, and try to understand what's been inundated, what's been flooded, how does this affect pasture, which affects livestock, different things like that. This is just a brief example of radar data. So in the images on the left, you can see an image of a hurricane over Texas in 2017. You can see clouds. You can't see through those, but on the right, you can see radar imagery from the exact same day, and that is penetrating those clouds. And so we can really see where water is standing in these fields. And that helps us to understand the water that's on the fields of certain types of crops that we want to know how they're affected. This is just an example of maps that come from those analyses. And we've been doing this since 2017 with various hurricanes, tropical storms, flooding events, and fires. Fires is on the next slide, which is just looking at fire perimeter polygons or burn scars and seeing what types of crops are encased in those perimeters. And we've been doing that since 2017 as well. And I believe those are the only examples I have right now, but if you want me to go into depth on any of those, I can, but that's all I have for you right now. So.
Thank you, Avery. All right. Can you?
Do you want me to stop sharing?
Well, it doesn't matter because you may need to reference a slide or something. The first question is, in establishing CDL, what source do you use for aquaculture? Is it survey, is it Sentinel, and how often is it updated?
Aquaculture should come from the same data set as all the other crops, which is the FSA, the Farm Service Agency, Common Land Unit data. I don't know anything, I don't know any specifics about aquaculture. It's in there, but I don't know any specifics about it.
Okay, and as you publish the results online, does it mean you publish 2 results of acreage for several crops, an area sampling frame and the remote sensing, and do you publish the CDL result each month?
So we do not. For the general public, for anyone outside of NAS, they only get the final product at the end of the year. That's it. For each month, those are all internal numbers. Those will go to our Ag Statistics Board, who sets the acreage or the estimates and the indications. They'll look at the CDL. We'll give them what we come up with from the CDL, how much they actually in their estimations. We don't know. That's something that is kept inside. They're not allowed to say.
I'll add to that a little bit. Plus, Avery, your audio was breaking up a little bit. At NAS, we only publish 1 number for acreage, production, etc. So the remote sensing information, this Cropland data layer, is a important piece of information that we use to determine the actual acreage of corn or soybeans, etc. So we're only publishing 1 number, and it can be informed by multiple sources of information, such as the Cropland data layer. Next question. As you publish, oh, no, I'm sorry, I just read that one, sorry. Do you have a problem from collecting data from other agencies?
We have problems. No, maybe someone else can answer this better on the call.
I'll give it a shot. No, we had to work through getting an agreement with, say, the Farm Services Agency. In the beginning, it was difficult getting data, not that they didn't want to cooperate, but more we had to match their location data with our location data and how we were identifying data. So there was just this initial, 10, 15, 20 years ago, difficulty doing that, but it wasn't that we had uncooperation from them. Since you have, sorry?
I'll add to that, Sarah. This is Rick. One of the things we do is we will look for partners in industry that will have useful data that will include that maybe they're not part of the FSA, the Farm Service Agency program. So for instance, we could be looking at the Washington State Department of Agriculture. They might give us apple inventory, which is not collected very well by a Farm Service Agency. We will look at U.S. Bureau of Reclamation. They do dam work, that's the hydroelectric projects. They collect irrigation information in Southern California, Southern Nevada. So it's going out and trying to find partners who have useful data. We also, I think we had in there the Utah Department of Water Resources. They had useful data, we included it. So we're trying to capture you know, the national picture, but if we can find localized information, we will add that into our process.
Thank you, Rick. Since you have multiple class classification, do you get the imbalance problem? If yes, how do you solve it?
The imbalance problem being what exactly?
Arif, can you explain that a little more? What do you mean by an imbalance problem?
Like overclassification.
Well, yes, we do overclassify, and we also underclassify different crops, different places, different years. And we account for that bias by doing the regression estimates, which is why we don't pixel count, because we know we're going to be overclassifying some areas. Sometimes you can visually see that there's a random water pixel somewhere or a random corn pixel in the middle of a lake or something like that. And so we do know we have overclassification, underclassification, misclassification. And that's all accounted for as much as we can by the regression estimates.
Thank you. Did you do Kriegering or any spatial technique to get no data area?
There is no data area. I think everything is just filled in. If it's missing from our agricultural land cover, it's filled in from our non-agricultural data. And that is not produced by USDA, but it does not have any no data. Like there are no areas of no data in our baseline non-agricultural NLCD product that we use.
Yes, like Avery was saying, each pixel has to have a home. So whether it's agriculture or non-agriculture, it's going to have to get fit into something appropriately categorized, the class.
Okay, thank you. One of the problems in a BPS project is cloud cover. Justin, who did the GADS talk, he gave suggestions to use SAR. Do you have any tips to solve cloud cover?
I have. Looking into radar has been a project before, especially in the earlier months that we do classifications. So in the spring, in June, we do have a lot more cloud cover issues than later in the year, just because of our climate. But we have looked into using radar data for those cloud cover issues. There is a paper out. I think what was found from that paper was that there was no difference in accuracy, or not a significant difference in accuracy between using optical data only and radar data. So we have done that research. That was recent. That was maybe 1 or 2 years ago. Yes, okay. But yeah.
But I'll add on is we used 6 medium resolution satellites last year. So we're bound to get clear acquisitions at some point during the week or within a 2-week period. In the US, we have a few areas that have a lot of clouds, maybe in the tropical areas of like Florida, but many areas, if we're hitting a particular pixel, 2 or 3 times every other day we're hitting it, we're going to get clear acquisitions. And what we're doing is we're just accumulating all these pixels for future analysis.
Yes, we use the full range of the season as much as we can every single time we classify. So if we're classifying in June, we'll use June data. If we're classifying in August, we'll use June, July, and August, and so on. So we use the full range every single time that we can to classify as well.
Thank you. I want to go back to the multiple class classification with the imbalance problem because I've got a better explanation of what the imbalance is. It's a problem that happens when every class doesn't have the same frequency. So it's an imbalanced frequency. Does that make sense?
I can try to jump in on this one. I think I understand what the question is being asked. So with the decision tree methodology that we use, we do really try to have a proportional sample of what we expect the land cover probabilities to be and what's generated at the end. So if 10% of the scene is corn and 90% is soybeans, we try to get about 10% of the samples as corn.
Yes.
Because they are definitely sensitive to those probabilities. So we do our best to get what we think is a proportional sample. We don't always know exactly, but we have a rough idea.
Okay,
Hey, Sarah, one other thing.
sure.
Zheng Wei, I don't think he's out there on the call tonight, but he has written a paper on this imbalance problem. So I will get a hold of him this week and share this with you so that you can share with the group. So on the imbalance problem.
That would be great. I'm making a note to myself on that. All right. Next question is, what feature of decision tree do we use? Do you use a multi-temporal feature?
For this one, I don't know exactly how to answer that one either.
I can jump in on that one too, Avery. I think the question is asking, or we both care about time and the multispectralness of the data. So time is certainly important. Some crops are planted slightly different. They react differently through the season. And then we also use the multispectral aspects of the imagery. So the visible bands, the near infrared band, the shortwave infrared bands. So it's both actually. But time, I think some of us would argue time is more important. So it's better to have imagery throughout the season rather than a couple good images with lots of bands. The time really helps us tease out crops. We just know that through experience.
Yeah, and C5, the software that we do use, allows an abundance of satellite imagery to be used in that classification process. So that helps too.
Great. Thank you. The paper that Rick had mentioned, he has added the link to the chat for everyone to be able to read at their own leisure. Next question is, have you studied the use of deep learning method to make more accurate classification than the current result?
Well, we've studied different ways to do the CDL. I know Dave is working on trying to do the CDL within Google Earth Engine, which I know you guys talked about last week, 2 weeks ago. Or I know BPS is using. I mean, we're always trying to improve it.
Yeah, I think the blunt answer is no. That stuff is still very, what we would call bleeding edge. So it's really unknown. People are really trying to figure it out. We aren't quite bleeding edge. I would describe us more as cutting edge. So we let people really be the pioneers and we take what they learn. But it certainly is out there and people are discussing it. But it's still, I think, unproven really at this point, to say it frankly.
One thing I'd like to add is we're an operational unit. So we can't have a neural network algorithm run for a week and to give us the best possible ultimate classifier. We have usually about 10 days, and some of that might be on a weekend, to get our algorithms through and derive a classification and make an estimate. So we need a system that's running fast and efficient to be able to produce our estimates internally for our boarding process.
Next question is, does the satellite imagery data and the ground checking data refer to the same time reference, the same date?
I believe this question is asking, does the ground reference data, does that get updated every time we do the CDL?
I think it's asking if they match. Does the satellite imagery data match the dates for the ground checking data?
Not exactly. So the ground reference data that comes from the Farm Service Agency, we get that data like on a certain day every month that we do the CDL. So in June, we'll get it like June 1. And so on June 1, we'll have whatever data was reported to the Farm Service Agency then. And we'll use any imagery in June, before June, around June. And then in August, when we do it again, the new ground reference data will be dated August 1st. So it's anything that's been reported up until August 1st now, and then we'll add the imagery from various dates up until August then. And so we get new ground reference data every time we do this. Better ground reference data.
I'd like to add one thing. So when these farmers are going to the office and reporting what they're planting, if they're doing a double cropping or triple cropping or quadruple 4 crops or whatever, they're telling the Farm Service Agency, they're signing up and saying, we put winter wheat in the ground in October or November of the year. And then later on in the year, they'll come back in and sign up and say, okay, in June of this year, we're putting in soybeans. So the ground reference is it's like an open database where they keep adding additional crops into their inventory. So we can capture whether it's a single planted field or it's a double crop or triple crop. We know what the signatures are in there.
Okay. This looks like it might be the last question. Could you explain in more detail the way you conduct ground check? And there's more questions after that.
So the way we conduct the ground like training and validation is we'll get the data set that is sent to us from the Farm Service Agency, and we'll look at the state that we're doing our analysis on. We'll divide that data set by fields. So about 70% of the fields from that data set will be used for training, and the remaining 30% will be used for validation. So you're never using the same, you're not double dipping, you're not using the same ground reference data for training and validation. They're all separate fields. And then we'll sample from those training polygons, those training fields, we'll sample, I don't even know how many points, like a million points or something, a million points from those training polygons, and it'll pluck points from cornfields, soybean fields, whatever it is. And that's what goes into our decision tree software, our classification. That's what we're trusting is correct, is right. And then once it's classified, those remaining 30 polygons that we saved for validation, we'll sample more points from those and just see if those validation polygons match what we mapped. And that's how we get our accuracies. Does that make sense?
I'd like to add one additional thing. Backing up from where Avery started, so we go through some cleaning algorithms up front when we get the Farm Service data. So the Farm Service data is provided to us in these large polygon files. And they also provide us attribute data, which gives us their what's been planted and how many acres are planted. So we're going to compare if a field, a polygon might say it's 50 hectares. And that's the polygon. But if the database says it's only 20 hectares, we can see that there's some kind of acreage discrepancy. And what we can do is we have so much good data, we'll throw it away. So there's a cleaning process that we'll go through. And we'll also look at planted date. If the planted date for a cornfield is 2 or 3 years ago, we'll ignore it. So there's ways of filtering and cleaning our data before we even start processing.
Okay, thank you. How do you deal with the narrow plantation area? Talking about the slide of grape commodity mapping. So
Yeah, that is a problem that we encounter as well, is small fields or narrow fields. And in our case, it really helps when a field is larger than the size of that Landsat 30-meter pixel. And when it's smaller than that pixel, it does get a little hairy. It's a little hard to distinguish, and that probably accounts for some of our lower accuracies. And like I said earlier on the accuracy slide, larger commodity crops that dominate the landscape. So in Iowa, we're only growing corn and soybeans. Those crops have a really high accuracy. But in upstate New York, there's really narrow fields, and those crops have a lower accuracy. How do we deal with that? I don't know. How do we deal with that? We will use ancillary data sets like the grape set that you mentioned, but it is a problem.
What about the buffering of the fields in the beginning?
Well, that would only be good for larger fields though, larger than pixel.
So we go through a cleaning process again on our ground data where we're buffering in 1 pixel to try to get to a clean field signature. So if a field is less than 60 meters across, it's going to get wiped away and not used.
Okay. And somewhat related is a question on how do you deal with the mixed plants in the same location? So multiple crops in the same field.
You know, I don't think I know that a lot of places in the world have mixed cropping. The US, I don't think is there a ton of that?
There's
Yeah.
a teeny tiny bit, like if you go out to some of the vegetable fields where they have different types of lettuce in the same field, or maybe, you know, they'll, like a red leaf versus a green leaf, or, you know, something like that. But in general, we don't have the same small fields that have 5 crops in it, or, you know, with one being a tree and so everything else is underneath the tree. We don't generally have that as a problem, as a situation. But how would you deal with that?
Higher resolution?
Yeah. Higher resolution, like Rick said. But that's hard to come by because that's not free. And yeah.
Would you ever do a classification instead of calling it crop 1 versus crop 2, just making it crop 1 and 2 together? Just sort of change your definition of the cropland? Would that be an option?
I mean, yeah, but you'd get a mixed signature that you really couldn't define, you know, what's the percentage of the bigger crop or the smaller crop. We just, yeah, you could estimate the area, but you can't estimate the specific crop.
Because I think this is really hit on one of the 2 big problems using remote sensing is how do you deal with very small fields, and how do you do with mixed cropping in a field? I know a lot of countries are trying to deal with it, and apparently there's no easy solution to that.
Correct.
All right, I don't see any more questions. If anybody has any more, oh, wait. If anybody has any more questions, you can send them to Oogie and she'll get them to us. Otherwise, thank you all very much. I love dealing with our spatial analysis folks because they obviously work together very well as a team and share information. So thank you all for that. Thank you, Avery. And thank you to BPS for your participation. And I hope everyone has a wonderful day or evening, as the case may be. We will be back with Avery Wednesday night my time, Thursday morning BPS time, and we will talk more about disaster assessment. All right. Well, have a wonderful day, everyone.
Thank you, Sarah.
Thank you.
Thank you.
Thank you.